Hey, what's going on guys? Tanmay here for Simple Snippets and welcome back to another tutorial on data structures and algorithms. And let's continue with our graph data structure topic that we have been going through in the last few videos in this DSA course. And today's topic is going to be adjacency list. Now before we proceed, I'm assuming you guys already know what is graph data structure and you've seen the previous few videos because this is like the continuation. So if you haven't seen that, I request you to go check out the last 2-3 videos in this DSA playlist, especially the adjacency matrix video and the graph introduction video, because as I mentioned, this is the continuation and you might not understand some things if you don't have a good understanding of what is a graph data structure and its different implementations. Okay. Alright. So having said that, I'm assuming you guys have already understood the previous few videos, the topics. Let's now talk about today's topic, that is adjacency list. Now, as I mentioned, graph data structure can be implemented in different ways when it comes to the actual practical coding side, right? And we have to understand the different ways in which it can be implemented to understand which is more suited in which scenarios. And that is the reason that we are first understanding the different types of implementations. Previously, we saw what is the adjacency matrix methodology of implementing a graph data structure, and you can see it on the left hand side over here. And one of its drawbacks, one of its major problems was that the space that it was occupying was to the power of 2. So the space complexity, as you can see over here, was O of n square, where n is the number of vertices, right? The number of actual nodes in the graph. So as the number of nodes increase, the space complexity increases to the power 2, which in real world scenarios is a lot, and you don't want this bad space complexity problem. So this is where the adjacency list comes into picture. We'll talk about time and space complexity in a minute, but let's just first understand what is adjacency list. So in an adjacency list, we use an array of list to represent the graph. So there are two data structures basically used over here. One is an array and one is a list. And this list, we'll talk about it with proper example, which is shown over here. I'll explain what is this in a minute. But just understand that adjacency list is very different from adjacency matrix. In adjacency matrix, you can see we have a 2D matrix which is storing individual edge values represented by zeros and ones depending upon whether there is a connection between two different vertices, right? So this is something that we've seen previously. But in a list, that is in an adjacency list, we do not store data like this. And here the size of the array is equal to the number of vertices, but the individual rows in this array represents the edges, okay? So an entry in the array A of I represents the list of vertices adjacent to the ith vertex. Now again, reading this theory will obviously make you go nuts and you'll be like, okay, this is confusing. This theory sounds a little difficult. But let's take a look at this adjacency list and then you can read the definition again and you'll understand everything properly. So what this adjacency list does is, just like adjacency matrix, the rows, that is this row 1, row 2, row 3, so on and so forth, represent the individual nodes or individual vertex. So 0 stands for A, okay? A is nothing but a node in the graph. You can take this graph for reference. Similarly, B is for index 1, C is for index 2. Now inside the first row, we don't have zeros and ones. You can see in the matrix we had zeros and ones depending upon the connection because the columns also were representing the same vertices. But here the columns are not really representing any of the vertices. So what are these columns representing? So you can see for the first row, which is for, as I mentioned, A, we have 1 and 2. So this 1 and 2 is nothing but the two other vertices that A is connected to. So A is connected to B and C. B can be represented by 1, right? You can see I have written over here in the gray also, and C is 2. So these are the numbers corresponding to the vertices that are connected to the first vertex A, which is represented by 0. Alright, if this sounds a little confusing, let's move ahead. Let's see the second row. Now second row is for B, right? Because B is represented by index 1. You can see over here also. How many other vertices are connected to B? You can see B is connected to A, B is connected to D, B is connected to E, and B is connected to C. So each of these other vertices also have their individual numbers, right? A is 0, so we have 0 over here. C is nothing but 2, so we have 2 over here. and 3 and 4 corresponds to D and E, right? You can see D is 3 and E is 4. So 3 and 4 are also there. So basically what this adjacency list represents is each row represents the vertexes that are connected to that particular index which is for that particular vertex. So for 0th row, we are talking about A, and we are talking about the connections or the neighbors of A. So who are the neighbors of A? 1 and 2, which is nothing but B and C, right? So in fact, I can just number them over here also, just for understanding purpose. A is represented by 0, B is 1, C is 2, D is 3, E is 4, and F is 5, right? Okay, so how do you represent this structure? Now you are wondering, okay, this structure doesn't look symmetrical, right? You can represent adjacency matrix in a 2D array. So how do you represent this? So this can also be represented using arrays, and if you've studied Java or C#, you might have heard of the concept of jagged arrays, right? Where the array is 2D array, but it is not having same number of columns in every row. Similarly, in C++ also you can implement this kind of structure using arrays by using the dynamic mechanism of creating pointers. So just to show you an implementation, what you can do is you can create a array of pointers. So int star arr would create an array which will store integer pointers. Right now I'm storing integer, that is int data type, because I'm assuming that the data we are storing inside each vertex is of integer type. It will of course be some class or some complex data type only, but for simplicity purpose I'm just taking int right now. So this int arr will be nothing but a array of pointers. So each index, that is index 0, 1, 2, 3, 4 and 5 will be nothing but a integer pointer which will store or which will point to the actual array which is created over here. So we are saying arr of 0 is going to be equal to new int 2. So in the memory, an array is created of size 2, and let's say the base address, that is the first address of this first cell, is hash 21. So hash 21 will be stored over here. Okay, so it will be pointing to this array in the memory. Similarly, this cell will store an address hash 31, let's say, which will point to the base address, that is the first address of the first cell in the memory. Let's say this is hash 31 in the memory. So individually you can see we are creating multiple arrays in the memory with different sizes depending upon the number of edges that are connected to that particular vertex. So 0 stands for A, as I mentioned. So for A we know that we have 2 connections, so that's why we have created an array of size 2. Alright, so this was just a quick explanation, and I know in the implementation, that is the coding side, you will still have a little bit of confusion. That is because we are still not yet started with the implementation, that is actual coding. When we do that, I will show you with the diagrammatic representation with the proper digital illustrations on how and what is going on behind the scenes when we write the code, just like we've been doing previously. But right now just understand that what we are doing is we are saving a lot of memory using this adjacency list, because if you see the adjacency matrix, remember that one of the biggest issue was that unnecessary space was being occupied by these zeros. So these zeros in the adjacency matrix represent that there is no connection between the two vertex. So A and D is not connected, right? A and D does not have a direct link, correct? So that's why there is a 0. But in the actual computer memory, this is just a waste of memory, right? We don't really need this. We only need the ones. And this is where adjacency list comes into picture. It is storing only those values that are having an actual connection. So for A, we only have 2 connections, and that's why we have only an array of size 2. For B, we have 4 other adjacent nodes. So that's why we only are occupying 4 memory allocations. So this is where, if you observe in the space complexity side, the space complexity of the adjacency list generally is O of E, where E is the number of edges. Now we are assuming that generally graphs have limited number of vertices and the number of edges are very less. So not every vertex is always going to be connected to every other edge, right? Typically in a real world scenario, as I mentioned, let's take an example of Facebook. Facebook has billion users. But are you friends with all the other billion users? No, you probably will have only 1,000 friends, right? Maybe 1,000, 2,000 friends. So you're not connected to all other users, which means that the number of edges is not that high. So that's what we are assuming. So this is where the space is saved, because we are not having extra zeros or extra values. We are only having the values where edges exist, right? Now talking about the time complexity, when it comes to finding all adjacent nodes, in adjacency matrix, we had to, go through the entire row to figure out the ones. Wherever there is one, there is a connection, right? So we have to go through the entire row. Similarly, for adjacency list also, we will have to go through the entire row. So if you want to find the adjacent nodes or the neighboring nodes of C, you will have to go through only these three array elements, right? So the time complexity is O of n, where n is nothing but the number of vertices, because maximum number of vertices a particular vertex can be connected is equal to n, right? Or n minus 1 basically, because A cannot be connected to itself. We are not considering self loops over here. So A can be connected to all the other vertexes, which would be n minus 1, right? So time complexity comes to O of n. Now in order to check if the two nodes are connected, this is where the adjacency matrix is a little bit faster, because in adjacency matrix, in order to check whether B and E are connected or not, you simply have to go to the index 1 and index 4 in this 2D matrix and check the value. Over here it is 1, so 1 means connected. So the time complexity is basically O of 1, because it will happen only in one single operation. That is because we will already have known what is the index or what is the actual index value for B and E. We will maintain a separate list, right? A separate list will be maintained for the index values. So you can quickly find out the index of B, which is equal to 1. You can store this in hash table like we saw in the adjacency matrix. So B is 1 and E is 4. So you simply have to go to ADJ of 1 and 4 and check if the value is 1 or 0. If it is 1, it is connected. If it is 0, it is not connected. So this operation will take constant time. So hence it is O of 1. However, this is a little tricky when it comes to adjacency list. Over here, since we are not storing the values in a 2D matrix, so let's say I want to find out if B and E are connected, right? So in that case, I'll either have to go and select B. I'll have to get the index of B, which is over here 1. So then I will go to this pointer, and now I will have to individually check each and every element in this array which corresponds to E's index. What is E's index? E's index is 4. So I'll have to go to 0. Is 0 equal to 4? No. Then I have to go over here. Then I have to go over here. And lastly, I will figure out, okay, 4 is there in this individual array for B, which means that B and E are connected, right? So this means I'll have to go through this entire row, which means that the time complexity is O of n. Now, if you have this list pre-sorted in ascending order, you can still apply binary search to search for whether E is there in the list of B, or vice versa. You can also go to E, that is index 4, and search for B's index, which is 1. So you can scan this also, since this is a undirected graph. And as I mentioned, if these numbers are in ascending order, you can apply binary search, which would reduce the time complexity to O of log n, right? We've talked about binary search separately in this playlist. You can check that out. Okay. So yeah, this is still pretty efficient. And now you have to figure out which type of operations are you going to do frequently. Depending upon that, you can use adjacency matrix or adjacency list, right? But one of the drawback when it comes to implementation using arrays in adjacency list is that we know that once we define the size of this array, that is this edge list, you cannot change it, right? Because arrays are static in nature. Once you define the size, you cannot change it. So imagine if there is a new connection happening between A to E. So what happens when this new connection happens? When it comes to adjacency matrix, you simply have to go to the index of A, which is 0. So 0th row, and E is 4. So fourth column, and this 0 you simply have to make it 1. Correct? So whenever a new connection happens, In adjacency matrix, it is easy to make that change. But what about adjacency list? In adjacency list, what you'll have to do is you'll have to create an extra cell in this first array. Now you've already declared the size by saying new int. You have to create a new extra cell and you have to add the number of e, that is index number e, which is 4, which will represent that a is now connected, that is there is a new edge between a and e. But you can't do this directly, right? Because you're implementing in the form of arrays, which means that now you'll have to create a new array. You'll have to create a temporary array, right, which will be of size 3, and then you'll have to copy the first two elements from this ARR of 0 and add this extra element. So ultimately you will have 1, 2 and 4, and now you'll have to make this ARR of 0 basically point to this temp. So you can see now this is a tedious process, right? This is not so straightforward. This is an indirect process which will take some time and it will have some extra cost. So this will definitely be bad in terms of efficiency. So how do you make this a little flexible without using the arrays? So this is where now you can use linked list. So we've also studied linked list and the different types in this DSA playlist. Go check it out if you haven't seen it already. But let's replace this structure, this array structure, which is very rigid, which cannot be updated. If there are new edges that are happening, or if you delete an entire vertex, then changing all these values is very difficult. So in that case, a linked list is much more flexible, and how that is flexible we'll see in a minute. So let me just show it to you. Alright, so I've replaced the array representation of adjacency list using a linked list, and let me just explain before you get a little confused. So now again we will create an array, that is an array of pointers, which will be of size 6, and 6 is corresponding to the number of vertices. But this time the edges, the values of edges and the connections basically are stored in the form of linked list. So these pink structures are nothing but individual singly linked list. So for 0, we've said 0 is a, right? So this is for a. Hash 32 is nothing but the address of the very first element in this first singly linked list. So this first singly linked list will be for all the connections of a. What are all the connections of a? B and C, right? So let me write B over here, or you can also write the value inside B, which is 54. That is your choice. And right now for representation purpose, I'll write B and I'll write C over here. So this second space is nothing but the address of the second node in this first singly linked list, which will have the value C, right? So let me write some address over here, hash 20. So this hash 20 will be nothing but the address of this second node, and this second node will have nothing over here, blank. So in case if there is a new connection, as I mentioned, in case if A now has a new connection between E, what will happen is we will simply have to add a new node over here, right? This will have E, and now the address, let's say it is created at address hash 17. These are all fictitious and fake addresses we are just using for reference. So this hash 17 will now be stored over here in this first singly linked list, and you can see now our linked list can be dynamically expanded, or let's say you want to delete a particular node, that is you want to delete a particular connection, you can completely erase this off later on dynamically using programming. Now we've seen those addition and deletion operations on linked list in this DSA playlist, you can check it out. But this makes the whole structure dynamic. Similarly, for the second index, that is the pointer, which are nothing but node pointers now. So node is nothing but our own class, right? Which stores data. So data can be any numeric value. Right now we are saying int data, which is 54. So each node is having a numeric data, but it can have multiple complex data also, and it is also having a pointer of its same type, which is pointing to the next node, correct? So this is how the singly linked list node is at a very basic level, and we are creating an array of type node, which means that each individual indexes, that is ARR of 0, ARR of 1, all of them are of type node. So they will be pointing to objects of node type only, and this is what they're doing. They're pointing to the very first node object in every list. So for ARR of 1, that is this is ARR of 1, right? You can see I have written ARR of 1. This will have some address, let's say hash 12. So hash 12 will be nothing but the address of the very first node in this singly linked list, which is, you can see, currently of size 4, because 1 corresponds to B and B is currently connected to 4 different other vertices, 1, 2, 3 and 4. So all those values will be filled over here. So you get the idea now, right? Now this adjacency list is now become much more dynamic or much more flexible when it comes to addition and deletion of different edges or maybe even an entire vertex, right? So this is the whole overview of adjacency list. The biggest advantage of adjacency list is, as I mentioned, the space complexity is equal to the number of edges and not to the number of square of vertices. And when it comes to time complexity, most of the operations have similar time complexity, just like adjacency matrix. Some of them, the time complexity is equal, some of them is efficient when it comes to adjacency matrix, but they are fairly similar, and hence adjacency list is used many times, especially when the number of vertices is not too high and the number of connections, that is the number of edges especially, is very less, right? Which means that we are talking about a sparse graph. A sparse graph is where the number of edges is very low or is considerably low compared to the different number of vertices, okay? So this is where adjacency list is considered more over adjacency matrix. Okay, so this was the entire adjacency list video. I hope you've understood this implementation of graph data structure, and we've compared it with the adjacency matrix also, so it was like a recap for you for the adjacency matrix as well. If you've understood this video, let me know in the comments how this video was. Do share it with your friends. These are important topics specifically for graph data structure. If you are new on this channel, check out the entire DAC course, check out this entire channel. There are a lot of videos. So I'm gonna wrap up this video over here. Thanks for watching. See you in the next one. Peace.